Two or more substances sometimes react together to form a completely new and different substance. The study of these reactions is a vital part of the science of chemistry. To understand chemical reactions, we must explore the most basic particles of matter. We call these basic particles atoms. We know that matter takes on many different forms, which suggests that there are different kinds of atoms. It would be useful to learn just how these atoms differ from one another. But identifying these differences is a challenging task because atoms are far too small to see. One possibility is that each different kind of atom has a different mass. If so, we could identify atoms by comparing their masses. The trouble is, no balance scale exists sensitive enough to mass a single atom. A balance scale would give us the mass of one atom in grams or kilograms. But just how useful would this information be anyway? Look at it this way. Suppose you are stranded in a strange, faraway place. You want to phone home, but the only coin you have is a plug, and it won't fit. So you need change. But what's the value of a plug? How much change will you get for it? Would it help you to know the value of a plug in terms of dollars or gold or even a barrel of oil? Well, they all may be valid, but they're not very useful to you at the moment. To get change, what you really need to know is exactly how the plug compares to other local coins. Think about your own coins. Each has a fixed value in relation to every other coin. We can express these relative values as ratios. These unchanging ratios allow you to work conveniently with money from day to day with any currency, whether foreign or your own. Now, what's all this got to do with atoms? Well, consider the mass of one single atom. Suppose we could just place it on a balance and find its mass in grams. The number is so small, so extremely small, in fact, it's hardly useful. Suppose then we ignore the mass of an atom in grams and simply compare its mass to the mass of other atoms as we compared the relative value of one coin to another. We might have a useful tool for studying chemical reactions between different atoms, a set of simple relative mass ratios. But how do we find the relative mass of an atom, or relative atomic mass, without first doing the impossible, massing a single atom to compare with others? There's a trick. Load a bunch of pigs into a truck and drive it to market. Now, suppose we want to know the mass of a single pig. How do we find it? It's not necessary to mass any one of them to find the answer. All we need to do instead is to mass the truckload. And of course, we have to subtract the mass of the container. Imagine we have 10,000 kilograms of pigs. The next step is to count the pigs. Let's say an accurate count gives us 50 pigs. All we need to do now is simple division. This gives us the mass of an individual pig, 200 kilograms. It's a very simple technique. First, find the mass of many items, count them, then divide. Now that we've found the mass of a single turkey, we can relate it to the mass of a single pig. This relative mass ratio tells us exactly how much greater one mass is over the other. But to find the relative mass of a single item, we still had to count many. And we'll never count billions upon billions of atoms to find the mass of one. So here comes the real trick. Take two truckloads containing equal numbers. Oh, never mind counting them. Just directly compare the mass of each truckload. The relative mass of the truckloads can be simplified to give us a ratio. And this is the very same ratio as the relative mass of the two single items. So, although we can find relative mass by comparing single items, the information is there, hidden in larger loads. Most important, under certain conditions, it isn't necessary to count the numbers in those loads. The first condition is that each load must contain only one kind of item. We then find the total mass of each load. Now, the second and most vital condition. The numbers of items in the first load must be exactly the same as in the second. It's only necessary to find the total mass of the second load, then directly compare the two total masses. The ratio will always simplify to the relative mass of two single items. Now, how can this fact help us with chemistry? The mass of a single atom can be a useful tool, a way of identifying different kinds of atoms, a way of telling them apart and exploring how they behave in chemical reactions. But at first, there seemed to be no practical way of finding the mass of each different kind of atom. One option was to mass a tremendous number of atoms, all the same kind, then count the many billions of them and divide. Really a hopeless way to find the mass of a single kind of atom. The other option seemed even more unlikely, comparing single atoms directly by creating some kind of supersensitive balance scale which could actually mass individual atoms. But now, potentially, we have another choice. Comparing the total mass of two equal numbers of items. This immediately gives us the relative mass of two single items. If we can do it with animals, why not atoms? The challenge is to somehow find a special truck for atoms, a kind of universal container. No matter what kind of atom in the universal container, we would need to be certain it always holds the same number. There would be no need to count them all or mass a single atom. We could directly compare two universal container loads on an ordinary balance. Because each universal container holds the same number of atoms, the relative mass of the container loads would always simplify to the relative mass of two single different atoms. Using this technique, we could build a table to record precise, measurable differences between atoms. Even though we can't actually see atoms or count them, it would give us a way of comparing different atoms in chemical reactions. Using relative atomic mass ratios, we would know with some precision which atoms have the least mass and which the greatest. A working table like this is certainly desirable, but can we actually find a universal atom container?